This video is continuing examples of finding the derivative using the limit definition. In our next example, we're going to find the derivative of y equals x cubed plus 2x. So our first step is to find f of x plus h, which would be x plus h cubed plus 2 times x plus h. So in order to do this, I'm going to have to multiply out x plus h cubed, and I already know what x plus h times x plus h is. It's x squared plus 2xh plus h squared. And now if I distribute this first x plus h, I'm going to end up with x cubed plus 3x squared h plus 3xh squared plus h cubed. And I will leave it to you to multiply that out and see that that is what it simplifies to. So my f of x plus h becomes x cubed plus 3x squared h plus 3x h squared plus h cubed. And we need to distribute this 2. We get plus 2x plus 2h, and I'm going to get rid of this to make some room. Now that I have my f of x plus h, we can plug it into the formula for a derivative, which is the limit as h goes to 0 of f of x plus h, which we just found, minus the original function, which is x cubed plus 2x, all over h. So now I'm going to distribute this minus, and I get x cubed plus 3x squared h plus 3xh squared plus h cubed plus 2x plus 2h minus x cubed minus 2x all over h. And I see, if I combine like terms, that x cubed minus x cubed will go to 0, plus 2x minus 2x will go to 0, and every term that I'm left with has an h in it, which if we've done this correctly, that's always going to happen, so that we can factor it out and cancel it with the h in the denominator. So this becomes the limit as h goes to 0 of h times 3x squared plus 3xh plus h squared plus 2, when I factor out that h, over h, which goes to 1. And we're left with the limit as h goes to 0 of 3x squared plus 3xh plus h squared plus 2. And when we substitute in h equals 0, this term goes to 0 and this term goes to 0. And we're left with the derivative is equal to 3x squared plus 2. Okay, let's try another example. In this example, we're using the function y equals the square root of x. So my f of x plus h is simply the square root of x plus h. So if we plug that into the formula for a derivative, then we'll get the square root of x plus h minus the square root of x, the original function, all over h. if we direct substitute h in here, I'll get 0 over 0, which we can't have, so we have to manipulate it. And we saw in an earlier lesson that when we're trying to manipulate square roots, we multiply by the conjugate. And the conjugate of the square root of x plus h minus the square root of x is the square root of x plus h plus the square root of x. So in the numerator, when I multiply this out, the middle terms are going to cancel because it's a difference of squares, and the first term is going to give me just x plus h. The outer terms will give me square root of x times square root of x plus h, but the inner gives me minus the same thing, so that goes away, and then my last gives me minus the square root of x times positive square root of x, so we're just going to get a minus x. And in the denominator, we leave that h out front because we want it to simplify out, which I see that it will. When I combine like terms in the numerator, all I have is an h. And so h over h goes to 1, and we get the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. We plug in a 0 for that h, and we get 1 over the square root of x plus the square root of x, which gives us our derivative. And if I go back to the notation I was asked to use here, we'll say dy dx equals 1 over 2 times the square root of x. Now at the start of this lesson, we learned that a derivative is the slope of the tangent line to the curve. So let's find an equation of the tangent line to y equals 2 over x at the point 1, 2. In order to do this, I'm going to need the equation of a line, and the equation of a line in point-slope form is y minus y1 equals m times x minus x1. So we need slope and we need a point. Well, we were given the point here, and we get slope from the derivative. So the first thing we want to find is our f of x plus h, and in that case, that's going to be 2 over x plus h. So our derivative is the limit as h goes to 0 of 2 over x plus h minus, the original function is 2 over x all over h. If we direct substitute in h equals 0, we're going to get 0 over 0. We have to manipulate this, and the way we do that with a complex fraction is to multiply the top and the bottom, numerator and denominator, by what would be the common denominator if we were to combine the two inner fractions. So I'm going to multiply top and bottom by x times x plus h. And when I do this, I have to distribute that to both the fractions in the numerator. When I multiply the first fraction by x times x plus h, those x plus h's cancel, leaving me with 2x. For the second fraction, when the x's cancel, I'm left with minus 2 times x plus h all over h times x plus h. And if I distribute that negative 2 there, we get the limit as h goes to 0 of 2x minus 2h over h times x plus h, and 2x minus 2x will go to 0, and h divided by h will go to 1. So what we end up with is the derivative is the limit as h goes to 0 over negative 2 over x times x plus h. We plug in a 0 for that h and we get negative 2 over x squared. So our slope is then the derivative evaluated at our point, and our x value is 1, so we get negative 2 over 1 squared is just negative 2 for our slope. So remember, our formula here is y minus y1 equals m times x minus x1, and our point is 1, 2, so that's our x1, y1, and we just found our slope. So when we plug into this formula, I get y minus 2 equals negative 2 times x minus 1, and that would be my answer if I wanted it in point-slope form. If I kept going, if somebody asked me to do it in slope-intercept form, I would distribute this negative 2, and then I would add 2 to both sides. And these are both good answers, and it's just in a different form.